Welcome my dear learners for this course on design of machine elements 2. In this module 2 we are discussing on design of springs. So far we have completed our discussion on design of semi-elliptical leaf spring. In today's lecture we are ready to discuss the design of belleville or disc spring and also the design of torsional spring. First let us discuss design of belleville or disc spring. The pictorial view or sketch of disc spring is available in your design data handbook in figure 11.1e referring to page number 168. These disc springs are used in high capacity operations where large amount of force is required to produce a small deflection. Example, it is usually applied in safety valves. Whereas in the top view, if you view this spring, it will look like a concentric disc, hence the name disc spring. Let us design this disc spring which is used in high capacity applications like safety valves where large amount of force is required to produce a small deflection. The problem number 18 of our discussion, which deals on design of disc spring, states that a belleville spring is made of 3 mm sheet metal with an outside diameter of 125 mm and an inside diameter of 50 mm. The spring is dished 5 mm. The maximum stress is to be 500 megapascal. Determine safe load carried by the spring, deflection at this load, stress produced at the outer edges, load for flattening the spring. Assume Poisson's ratio as 0.3 and Young's modulus as 200 gigapascal. And one more important thing is that in case of disc spring, the stress induced will be maximum at inner edges, whereas at the outer edges it is comparatively less when compared to inner edge. So therefore, what he has specified, the maximum stress is to be 500 MPa is at inner edge of this disc spring. Let us design this disc spring. If I list out the data given, we have the thickness of this disc spring is 3 millimeters. It has an outer diameter D0 which is 125 mm and inner diameter DI which is 50 millimeters. The spring is dished by 5 mm, that is H is 5 mm. Since he has given maximum stress, that is sigma I, which is 500 megapascals. Now let us solve this problem. Since he has given us the maximum stress, that is stress at inner edge, let us use the formula for stress at inner edge and find the deflection. That is, we have from equation 11.33b, the stress at inner edge is given by sigma I is equal to 4E y divided by 1 minus mu square m d0 square of C1 into H minus y by 2 plus C2 times thickness. This is equation 11.33b. Now we have the constants m, C1 and C2 which are constants which are the function of dA and d0. So therefore, first let us find the constants m, C1 and C2. To find constants, if I take constant m is given by 6 divided by pi ln d0 by di of d0 by di minus 1 whole divided by d0 by di whole square. This is equation 11.33b of page number 183. So we know all the values. If I substitute and solve, I will get constant m as 6 divided by pi times ln 125 divided by 50 multiplied by 125 by 50 minus 1 whole divided by 125 by 50 whole square. So therefore the value of constant m will be 0.75. So the value of constant m is 0.75. Moving for calculation of constant C1 and C2, we have constant C1 is given by 6 divided by pi ln d naught by di whole multiplied by d naught by di minus 1 divided by ln of d naught by di minus 1. This is equation 11.33e. So if I substitute and solve, I will get the value of C1 as 6 divided by pi ln of 125 by 50 multiplied by 125 by 50 minus 1 whole divided by ln of 125 by 50 minus 1. So if I solve, I will get the value of C1 as C1 is equal to 1.328. Now calculating the value of C2, I will get C2 is equal to 6 divided by pi ln d naught by di minus 1 whole divided by 2. This is equation 11.33f. So if I substitute and solve, we get the value of C2 as 6 divided by pi ln of 125 by 50 125 by 50 minus 1 whole divided by 2. So therefore C2 will be equal to 1.563. So we have calculated the constants m, C1 and C2. Now substitute this equation and find the value of deflection. I will get sigma is given as 500, which is equal to 4 times Young's modulus is 200 into 10 to the power of 3 into deflection is what I should calculate, divided by 1 minus mu is specified as 0.3. It is Poisson's ratio square. M is 0.75 into d naught is 125 whole multiplied by C1 is 1.328 of H is 5 mm minus deflection by 2 plus C2 is 1.563 into thickness is 3 mm. Now you have to find the value of y. I should get two answers because it is a linear equation of degree 2. So now one more important note is that we have height h as 5 mm, so therefore deflection cannot exceed 5 millimeters. Deflection cannot exceed height 5 millimeters. So deflection should be within 5 millimeters. At 5 millimeters, this disc spring will become flat. So therefore y cannot exceed 5 mm. So in order to find it, two answers of y, let me formulate the equation. I will get 500 into 1 minus 0.3 square into 0.75 into 125 square divided by 4 into 200 into 10 to the power of 3. So the value of constant is 6.665. 6.665 will become the constant, and then I have 1.328 into 5 y plus 1.563 into 3 y. It will be 11.329 y. 11.329 y minus 6.665 is the value of constant. So here I will get the value of y square as 1.328 divided by 2, 0.664 y square. This is equal to 0. Now moving for equation mode, taking 3, that is degree 2 equation, we have 0.664 y square, 11.329 y minus 6.665. Sorry, here we have missed the negative sign. This is minus y square by 2 into 1.328. So this should be negative. So that is minus 0.664, 11.329 minus 6.665. So we get the value of y as y is equal to 16.45 mm and y is equal to 0.61 millimeters. So since y should be less than h, adopt y is equal to 0.61 mm. We can't take this. Now we got the value of deflection. Next, moving ahead, first one, safe load carried by the spring. So we calculate the first quantity what he has asked, that is safe load carried by the spring. We have formula for safe load given by F is equal to 4EY 1 minus mu square md naught square of h minus y of h minus y by 2 into t plus t cube. This is equation 11.33a. So referring to equation 11.33a, if I substitute and solve, I will get 4 times 200 exponential 3 into 0.61 divided by 1 minus 0.3 square into m is 0.75 into d naught is 125 square into h minus y, 5 minus 0.61 into 5 minus 0.61 by 2 into thickness is 3 mm plus 3 cube. So therefore the safe load is 4065.1 newtons. Next, second quantity is deflection at this load. Now if I calculate the deflection at this load, we have already calculated it and found out to be 0.61 millimeters. The second quantity is done. Moving for third one, stress produced at the outer edges. So deflection is 0.61 mm. Stress produced at outer edge is given by 4E by divided by 1 minus mu square m d naught square of C1 of H minus by 2 minus C2T. This is equation 11.33C of page number 183. So if I substitute and solve, I will get sigma naught as 4E by divided by 1 minus mu square m d naught square is done. Now we have C1. C1 is 1.328 into H is 5, Y is 0.61 by 2 minus C2 is 1.563 into thickness is 3 mm. So I get sigma naught as 70.745 megapascals. You can see at the inner edge we have 500 megapascal, at outer edge we have 70.745 megapascal. Coming for the last one, load for flattening the spring. So for flattening the spring, if this spring becomes flat, then deflection is equal to H. So use the condition H is equal to Y. So use this flattening condition in equation 11.33a. So from equation 11.33a we will get load F is equal to 4EY divided by 1 minus mu square m d naught square into H is equal to Y. This will become 0. 0 into anything is 0. So I left out with T cube. So therefore, load for flattening for maximum deflection will become, here Y should be equal to so answer is 10127.5 newtons. So this is the load required to flattening of this disc spring. So this is the complete solution of design of belleville or disc spring. Let me pause this video for a while so that you people can copy it down. Later we will solve helical spring in torsion. Now moving ahead, next is design of helical torsion spring. So this is a pictorial view of helical torsion spring which is subjected for bending and torsion, which is given in a design data handbook in figure 11.1d page number 168. Let us solve a problem on helical torsion spring. The problem number 19 of our design on springs states that a helical torsion spring of mean diameter 50 mm is made of a round wire of 5 mm diameter. If a torque of 5 Newton meter is applied on this spring, find the bending stress, maximum stress and deflection of the spring in degrees. Take modulus of elasticity as 200 GPa and number of effective turns is equal to 10. Let us solve this problem. If I list out the data given we have for problem number 19, the data is mean diameter, that is capital D, is 50 millimeters, made up of round wire. So wire diameter is 5 mm. If the torque T is 5 Newton meter, so therefore T is equal to 5 into 10 to the power of plus 3 newtons millimeter. Find the bending stress, maximum stress, and deflection in degrees. Take modulus of elasticity as 200 into 10 to the power of 3 megapascals and active number of coils as 10. So this is the data given. So now if I solve this problem, directly move for page number 179. From equation 11.24 we have maximum stress equation given by maximum stress sigma is given by Kt by Z plus 2T by dA. This is equation 11.24 A, referring to page number 179 of our design data handbook. So this equation remains same for both round wire as well as for rectangular cross section wire. Only difference is that we should change the value of K, Z and area. So coming for the value of K, K is equal to K1 for circular cross section wire, K is equal to K2 for rectangular cross section wire, from figure 11.3 page number 169. Now K is equal to K1 for circular wire from figure 11.3 referring to page 169. Referring to page number 169, figure 11.3, K is equal to K1 for circular wire, K is equal to K2 for rectangular wire. We are solving for circular wire. So if I refer that figure, we have stress factor K varying from 1, 1.1, 1.2 like this, versus the spring index 2, 3, 4, 5, etc. to 10. And we have K1 varying like this. We have K1 line somewhat varying like this. This is spring index. This is stress factor. So therefore, if I take from the graph and get the value of K, which is above 1.5, nearing to 1.9. So therefore, from this figure 11.3 for C is equal to D by D, which is equal to 50 by 5, which is equal to 10, K which is equal to K1, which is equal to 1.08 I can take from the figure or from the graph. I'll take it as 1.08. Now this term will indicate the bending stress. So I was asked to calculate the bending stress separately. So therefore, calculating the bending stress separately, bending stress, we have sigma bending is equal to K1 T by Z Z is equal to pi d cube by 32, which is nothing but section modulus. So therefore, if I calculate, I'll get bending stress as 1.08 into 5 into 10 to the power of 3 divided by 5 times diameter is 5 cube divided by 32. So therefore, bending stress for this problem is 1.08 into 5 into 10 to the power of 3 divided by 5 into d to the power of 3 divided by 32, which is 440.03 megapascals. Now, if I calculate the maximum stress, sigma is equal to sigma bending plus 2 times torque divided by dA. So therefore, sigma max will be 440.03 plus 2 times torque is 5 into 10 to the power of 3 divided by diameter is 50, area is pi d square by 4, pi d square by 4. So therefore, maximum stress will be plus 2 into 5 exponential 3 divided by pi d square by 4, which is turning out to be 450.22 megapascals. So this is the maximum stress. So we have calculated the maximum stress. Now he is asked to calculate the deflection in degrees. So first let us calculate the deflection. We have deflection given by torque length into diameter divided by 2 times Young's modulus into area moment of inertia. This is equation 11.24b. So therefore, we know all the values. So we know that overall length can be taken as pi di, which is equal to pi times 50 into 10, which is equal to 500 pi millimeters. So therefore, deflection will become 5 into 10 to the power of 3 into 500 into pi into 50 divided by 2 into Young's modulus is 200 exponential 3 into moment of inertia for a circle is pi d power 4 by 64, pi d power 4 by 64. Therefore, deflection will be pi exponential 3 into 500 into pi into 50 divided by 2 into 200 into 10 to the power of 3 into pi into 5 to the power of 4 divided by 64, which is nothing but 32 millimeters. Now, we already know that if I consider spring deflection, which is subjected for torsion, if I apply a torque T with compression, we have deflection theta, and this distance is d by 2. If I take this as deflection, so therefore I can write deflection as also deflection is equal to theta into d by 2, where theta will be in radians. That is 32 divided by d by 2. D is 50 by 2, that is 25. It is turning out to be 1.28 radians. 1.28 radians. So therefore, in degrees, theta will be equal to theta radians into 180 by pi degrees. So therefore theta in degrees will be 1.28 into 180 by pi, that is 73.34 degrees. So 73.34 degrees is the deflection. So this is the complete solution for helical spring in torsion. This completes our discussion on disc spring and helical torsion spring. In our next lecture, I will take up helical spring substitute for fatigue loading. That's all from this lecture. Thank you all.